This is Physics 2212, Lab 3, going over the magnetic field of a bar magnet. Now in this lab, we will be understanding the concept of magnetic dipoles and visualizing the magnetic dipole of a small bar magnet. And then we will be using the Biot-Savart law to understand how distance will impact the observation of an electric field. And preview results, we get the off-axis field to be about 4.75 times 10 to the negative fifth Teslas. Now, in the procedure, essentially, we will be first determining where the magnetometer sensor within a phone is by essentially checking different distances and different values of microteslas. And then we will be, and as well as orienting it along an axis um, to find where north is. And then we will be, after we find the magnetometer, we will be finding the distance between the magnet and the magnetometer at different values of microteslas. And then we will be recording each component of the magnetic field. And down below is the Biot-Savart law that we'll be implementing for the entirety of the lab. Now these are the observations realized. So as you can see, we recorded the distance at different values of microteslas, and it was important to remember that everything was measured in microteslas originally, but we did have to end up converting to Teslas for it. And then also when we did it, we actually used centimeters and had to convert to meters. So we also had to consider in this the actual magnetic field of the Earth and had to correct for that. But also one thing that we didn't necessarily correct for, but it does cause influence, is just, the surroundings we're in. We did this in the GPS classroom, so it was kind of hard to get a, uninfluenced set of results, when you have stuff like metal brackets going on and then laptops. It was kind of hard to record the data and then be able to switch to the magnet in the phone without getting any sort of interference there. So keeping that in mind, that there is some influence for that, but we were still able to keep pretty close to the standard value for what we should have been getting for Atlanta. Now for the observations, when the magnetometer is far away from the magnet, it measures about a near zero magnetic field in the x direction. And then the position of the magnetometer has no effect on the measured x component of the magnetic field. And then as the magnetometer will move closer to the magnet, the measured x component of the magnetic field will increase as you expect. Now this is the code actually visualizing the magnetic field of the bar magnet. So as you can see here, we pretty much just essentially use the cylinder to create the bar magnet at the origin, and then go on to create a function to create the magnetic field, and then visualize that on axis and then perpendicular to the axis. Um, and then using the values gathered from the lab, and then pretty much visualizing it also at a 45-degree angle off of the axis to see what that would look like. And this is what that visualization looks like, and the different values calculated from it can be seen at the bottom. Now, what if we hadn't oriented the experiment to compensate for the magnetic north during the procedure? Essentially, we just get less accurate data, and so the readings would be more invalid because you have, some sort of influence by the magnetic north that isn't necessarily accurate to your data. And then also, what if we had stuck two identical magnets together and it ran the experiment again? Well, the field would be the same, but the magnitude would be approximately double. And, we could see this when we actually tried it. We were just goofing around and we actually stuck two magnets together and then tried it, and we saw that the magnetic field uh, increased approximately by double what it was. Thank you.